Our topic for this week is graph theory. Graph theory is a huge subject, and unfortunately we're only going to have time to scratch the very surface of it. In computer science, graphs and graph problems and graph algorithms come up all over the place. In artificial intelligence and machine learning, they come up in representing state spaces and plans for artificial agents, and also in representing the computation that happens in a neural network. In hardware or systems settings, graphs can represent the layout of a circuit or the connectivity of a computer network. In theory of computation and algorithms contexts, graph theory comes up in a huge fraction of the problems and algorithms that we study, and graphs are a fundamental building block of our models of computation. On the math side, we have an entire course dedicated to graph theory, and graph theory also appears as a small part in many other classes. And outside of math and computer science, graphs come up in all sorts of other fields, ranging from social sciences to engineering. Sociologists use graphs to study social networks, and economists use graphs to study credit relationships. And an electrical engineer might use a graph to model a power grid, while a civil engineer might use a graph to plan infrastructure connections. So our goal for this week is to lay down some fundamentals of graph theory with an eye towards setting you up for the things you might see in graph theory, Math 325, or analysis of algorithms, Comp Sci 321. Today we're going to begin with a whole bunch of definitions, and I'll illustrate many of those definitions with one of my favorite examples that comes from machine reasoning. As I mentioned before, in artificial intelligence contexts, graphs are often used to represent state spaces, where we have vertices representing states of the world, and edges representing transitions between states that a robot or other agent could cause. In the simplest case, this might look like a robot navigating in a building, where the state might involve what location is the robot currently in, and a transition between states would mean the robot moving from one room to another. And so this map of a small building can be represented by a graph made up of a vertex for each of the rooms in the floor plan, and an edge connecting two vertices if it is possible for the robot to move from one of those rooms to the other. And in an artificial intelligence context, we might use this graph to build a plan that will help the robot accomplish some goal, like pick up the ball and bring it to room A, where the robot would have to figure out how to navigate from its current position to where the ball is, and then from there to room A, and such a plan would correspond to a path through the graph that would get the robot from its starting location to vertex D, and then from vertex D to vertex A. But this same graph, this same collection of vertices and edges, could also model many other things. For example, this graph could represent a social network where the vertices correspond to people and the edges correspond to friendships between them. And so this could illustrate who knows who or who's friends with whom at the beginning of the semester in a small Davidson class. And so from here on, we're going to focus on the abstract representation in terms of vertices and edges, with the knowledge that there are many different types of things that a graph like this could represent in different contexts. When we're talking about graphs, we will generally represent them visually in terms of this sort of drawing, where we show the vertices as circles and the edges as lines connecting them. But our mathematical definition of a graph is a set of vertices and then a set of edges where each edge is a set of two vertices. So for this graph, we can write down the representation as a set of vertices and a set of edges as follows. So our set of vertices is just the nodes A through H in our picture, and our set of edges is the pair of vertices AH, indicating that A and H are connected, BC, indicating that B and C are connected, and so on. In our definition here, we said that the edges are a set of two-element subsets of the vertices, but here I've abbreviated those two-element subsets by throwing away the curly braces and the comma, since there are so many of them to write. In the definition of a graph, I've pointed out that we are specifically talking here about simple, undirected graphs, and both of these give us our particular definition for the set of edges. An undirected graph is one where there is no directionality to the connections. If instead I drew these connections as arrows, where, for example, we had an arrow from A to H, that would indicate that there is a directed relationship between A and H, and that would give us a different type of graph. We would model a directed graph by having the edges be ordered pairs, where the edge A points to H would be a different ordered pair from the edge H points to A. Simple means that there are no self-loops, that is, edges going from a vertex back to itself, and there are no parallel edges, where there are two edges between the same pair of vertices. And that factors into our definition of the edges, because we said that there must be two elements in this set representing an edge, whereas a self-loop would only have one element, and that the overall collection of edges is a set, meaning that there can't be any repeats of the same edge. Many other variations on graphs are also possible. For example, weighted graphs, where numerical values are associated with certain edges or vertices. But for our purposes, we're going to focus on this definition, where we have a simple graph with a finite number of vertices and undirected edges. Since our primary goal for today is to establish the vocabulary that we will use to talk about graph theory, I'm now going to give a bunch more definitions. But I'll also try to illustrate each of these definitions using examples on this graph. Graphs are all about representing relationships between the objects that are vertices, and so we will often want to talk about those relationships, where we say that two vertices are adjacent when there is an edge between them. And we can indicate adjacency with this relation. So two vertices are related by this operator if there is an edge between them in the graph. And if two vertices are adjacent, then we say that they are neighbors. And so as an example, in this graph, we have that G and F are neighbors, but G and A are not neighbors. We can also talk about the set of vertices that are neighbors of a given vertex, and we call that set the neighborhood. So the neighborhood of G is all of the vertices that are adjacent to G, which in this case is F and H. And we use capital N to indicate the neighbor function that for a given vertex gives us the set of neighbors of that vertex. And we will often subscript that with a G so that we know which graph we are talking about a neighborhood within. The degree of a vertex is the size of its neighborhood. We denote this with D sub G. And the size of the neighborhood is equal to the number of edges incident to that vertex. So the degree of node G is 2, since it has two neighbors. And the degree of H is 6. Even though we're focusing on undirected graphs here, because directed graphs come up often enough in computer science, it's worth pausing for a moment to think about how these definitions would differ in a directed graph. Remember, a directed graph is one where we have ordered pairs for our edges, so each edge has a direction. A good example for thinking about the difference between a directed graph and an undirected graph is Facebook friends versus Twitter followers. On Facebook, friend relationships have to be mutual, where both parties have to accept for there to be a friendship relation. And so that's modeled by an undirected graph, where if G is adjacent to H, we also have that H is adjacent to G. So in an undirected graph, our adjacency relation is symmetric, whereas on Twitter, it would be possible for person G to follow person H, but person H to not follow person G. And so we would have a directed relationship where the pair GH would be an edge in the graph, but HG would not be in the graph. And that would mean that in a directed graph, it is not necessarily the case that U being adjacent to V means that V is adjacent to U. Likewise, in an undirected graph, the sort that we will be focusing on, we know that if H is in the neighborhood of A, then A is also in the neighborhood of H. But that would not necessarily be true in a directed graph. And so in a directed graph, we would need to define the neighborhood and the degree of a vertex differently. But focusing on the undirected graphs we've defined, what is the sum of all of the degrees in the graph? If we were to add up the degree of A plus the degree of B and so on for all of the vertices, can we come up with a formula for the total degree? I claim that the sum of degrees in an undirected graph is twice the number of edges. And we can give a combinatorial proof. We want to argue that this sum is counting every edge twice. Every edge in the graph has a vertex on either end, so those are the vertices that the edge is incident on. And so for each of those two vertices, the edge will contribute to the degree of that vertex. So for every edge, if we think about the two vertices that it's incident on, each vertex will appear in the neighborhood of the other. And since the degree is the size of the neighborhood, that means that this edge is contributing 1 to the degree of u and 1 to the degree of v. And so then when we sum up all of the degrees, it will have contributed a total of 2, and we'll get 2 times the number of edges as our sum of degrees. In a minute, we're going to talk about subgraphs, where we take a subset of the vertices and edges in a graph. And one of the things that we'll look for in subgraphs is complete subgraphs. So to set up for that, let's define what we mean by a complete graph. A complete graph is one where the set of edges includes every pair of vertices in the vertex set. That is, it contains every possible edge given the set of vertices. A complete graph with n vertices is referred to as k sub n. And really, there's only one complete graph with n vertices, because any two graphs that are both complete and have the same number of vertices are isomorphic. That is, we can convert one to the other just by relabeling the vertices. So k sub 4, for example, is the graph with 4 vertices where each vertex is connected to all 3 of the others. And part of where we're going with this is that we might want to look for complete subgraphs within a graph, where we might pull out a subset of the vertices and the edges between them. So if we pull out GF, we have a complete subgraph, but on the other hand, if we pull out G and A, we don't have a complete subgraph. So let's define clearly what we mean by a subgraph. A subgraph of G is another graph H where the vertices of H are a subset of the vertices in G, and the edges of H are a subset of the edges in G. So we can get a subgraph by deleting edges or deleting vertices, but of note, when we delete vertices, we need it to be the case that H is still a graph. So if we deleted a vertex, we would also need to delete from the edge set any edges that were incident on that vertex. So we would need to delete these edges as well. There are some names for different types of subgraphs resulting from deleting certain edges or vertices, but we'll focus on induced subgraphs that are produced specifically by deleting some of the vertices and then only deleting the edges that we have to delete in order to have it still be a graph. An induced subgraph is specifically the graph that we get when we delete some of the vertices. So we have A as a subset of our original vertex set, and then we preserve all of the edges that we can between any vertices in the subset A. So every edge that is between two things in our subset of the vertices will appear in the induced subgraph. So for example, on this graph, if we build an induced subgraph with the subset of the vertices ABC, FG, then we would need to include every edge that's between two of the vertices in our subset. And so in our subset of the vertices, we've deleted D, E, and H. So we have to throw away all of the edges that are incident to any of those vertices, and we keep all of the edges that are between two things in A, but that, in this case, is just the edge between B and C and the edge between F and G. And so this is our induced subgraph. But we could also think of our original graph as having been an induced subgraph of a much larger graph. For example, when we were thinking of this graph as friendship relationships within a particular class at Davidson, we could think of the full graph as all friendship relationships among all Davidson students, and then we choose the subset of the vertices that are students in this particular class, and then we throw out all of the edges from these vertices to vertices that are not in our subset. So many of these people have more friends than they do in this graph, but those were not part of the subset of the vertices we chose. And so when we just preserve the edges within the vertices we've chosen, this is our resulting induced subgraph. So we motivated this with the idea that we were going to want to look for complete subgraphs. So let's define our terms again. A clique within a graph is a subset of the vertices in that graph, where when we build the induced subgraph, we get a complete graph. Equivalently, we could define a clique as a subset of the vertices such that all of the vertices in that subset are adjacent in the graph. In this graph, or any graph, every vertex by itself is a clique of size 1, because we saw that the complete graph of size 1 was just a singleton vertex. For every edge in the graph, we have a clique of size 2, because we saw that the complete graph on 2 vertices was just 2 vertices that are adjacent to one another. So we have many size 2 cliques in the graph. Where the definition gets more interesting is when we're looking for cliques of size 3 or larger. A clique of size 3 is 3 vertices in a triangle that are all adjacent to one another. So we have 2 cliques of size 3 here, F, G, and H, and B, C, and H. In this graph, we don't have any cliques of size 4 because if we pick any 4 vertex subset, at least one of the edges would be missing, and so there are no induced subgraphs of size 4 that are complete. The clique number of a graph is the size of its largest clique, which we denote with the Greek letter omega. And so in our example graph here, since we said there is a clique of size 3, but there is no clique of size 4, it has clique number 3. So we're now set up to ask an interesting problem, namely, given a graph, find its clique number. And if you take analysis of algorithms or theory of computation, you will likely prove that this is a hard problem. Specifically, it is a hard problem in the sense that, unless some things that we believe are probably true turn out to be false, there cannot be an efficient algorithm for solving this problem on an arbitrary graph. What it means for an algorithm to be efficient in terms of analyzing the runtime as a function of the problem size, and the proof technique for showing that this problem is hard are things that you would study in depth in upper-level computer science theory classes. So if finding the largest clique is a hard problem, then maybe we can think about what is in some sense the inverse problem. Namely, instead of looking for subgraphs where all of the vertices are adjacent to one another, maybe we could look for subgraphs where none of the vertices are adjacent. An independent set is a subset of the vertices where none of the vertices in that subset are adjacent to one another. So if we were to build the induced subgraph, we would get no edges between those vertices. So for example, an independent set would be A, C, E, and G, because A is not adjacent to C, E, or G, C is not adjacent to A, E, or G, and so on. And just like we defined the clique number as the size of the largest clique, we can define the independent set number as the size of the largest independent set. And we use the Greek letter alpha to refer to the size of the largest independent set. So for this graph, we know that the independent set number is at least 4. And so we should ask, is there an independent set of size larger than 4? By inspection, clearly H can't be in a large independent set, because if we include H, the only other vertex we could include is D. And if we're excluding H, then we can always include A, because it's only adjacent to H. And we can always include one of G and F, but not the other. And among B, C, D, and E, we can include 2 of them, for example, BD, or BE, or CE, but there's no way to include 3 of them. And so in fact, 4 is the size of the largest independent set, which gives us the independent set number of the graph. And we could likewise define the problem of, given a graph, find its independent set number. And I challenge you to think about how you would solve this problem algorithmically, and also to think about the connection between these two problems of finding an independent set number or finding a clique number for a graph.